Okay, welcome to our second live Q&A session for Astronomy State of the Art. I'm glad to see, well, I can't see you, but I know there's dozens of you out there, and some great questions have been coming up on the website, on the Udemy site, which I hope we've been keeping up with. I'm ably assisted, you can just see me, but I'm ably assisted. Matthew's been working the technology, which is finicky, as you can imagine. All of these video chat technologies are new and evolving. And I'm also joined by all my preceptors, so I'm going to actually take a minute and introduce them. That word may be unfamiliar to you. Preceptor means undergraduate teaching assistant, and it means they're formally part of the course and doing this for credit with the University of Arizona, and have been helping since before we started, actually. So I think you'll be able to hear them on the audio feed, so I'm going to ask each of them just to say who they are and what their major is, and so you know, even if you can't see them.
I'm Felicia.
And you do give your major and what you're interested in. Just speak up, just speak loudly, and they'll be hearing.
I'm actually undecided, and I took a great interest in astronomy, so I volunteered to precept for this class.
Okay.
My name is Kendall, and I'm a philosophy, politics, economics, and law major, and I've always just really loved science.
That's like the opposite of being undecided. That's like too much. Deciding too much.
I was gonna say, isn't that about the same thing as being undecided?
Yeah, maybe.
I'll just pick everything.
My name's Ross, and I am currently a music performance major on bassoon, and I'm looking to add a second degree in astronomy.
And I can just interrupt here. Yes, I'll anticipate some questions. Yes, we will have Ross with his bassoon at some point. Maybe at the end of the course. We're going to have a little celebration after all.
I'm Andrea, and my current major is engineering, but I'm going to switch to chemistry.
Okay.
I'm Michael. It'll show up as Charles in your chat window. I'm a finance major with a strong side interest in amateur astronomy.
Okay, it's a great team, and let's just get started. So questions have been coming in, and I'm going to have them read out so we can answer them. Anyone can start.
So the first question is, can you quickly just talk about the detection method of gravitational microlensing?
Right. I didn't give that serious play in the video lectures. It was referenced on the slides, I think, because it's a niche technique, and it has only really found a couple of dozen exoplanets. And since we know of a couple of thousand, you might think, well, why bother? Why should we even care? But it's a very important technique. Well, first of all, it's clever. So how does it work? It works because microlensing is a phenomenon that was predicted as an outcome of general relativity back in 1916 when the theory was first published. And gravitational lensing of any kind wasn't observed until the late 1970s, and microlensing not until the 1980s. So it took a long time for this to be observed. Microlensing is a situation where within our galaxy, one star just happens to pass in front of another more distant star. They're unrelated, they're not in orbit around each other, they're just drifting through the galaxy. And if that passage is almost perfect, the star passes directly in front of the more distant star, then according to relativity, the light of the background star will be amplified. Also, the light will be bent, but that bending angle is a micro arcsecond or so, and that's where the name microlensing comes from. There is lensing geometry, but the deflection angles are so small you couldn't resolve them with an optical telescope. So all you see with an optical telescope is a star that you're staring at suddenly brightens for a little while, and that's the lensing signature. And it's quite particular. It's to be distinguished from almost any other kind of variability that a star might undergo. So there's lensing as an effect, and it's been observed dozens, maybe hundreds of times since the 1980s. And people realized at the time that this technique is very sensitive to fairly low-mass stars that are drifting in front of more distant stars. They also realized that in the situation where a star passes in front of another star and the light of the background star is amplified, there could be a planet attached to that foreground star, and the light of the background star would be amplified by a much smaller amount by the planet around the foreground star. So if planets are in orbit around stars in general, microlensing of one star by another should be accompanied by a smaller signal from the planet around the star. And that was predicted, and then it was finally observed maybe 15 years ago. Well, this is a long-winded way of saying that now that technique is producing a steady little trickle of planet detections. Why is it important? It has a huge strength and a huge limitation. The limitation, as you can understand, is that not many planets have been found this way, because the probability of any two stars passing one directly in front of the other is about 1 in a million. So essentially you have to study 1 million stars to find one that will do microlensing. That's much harder than the Kepler experiment, which is looking at 100,000 stars and will find hundreds of cases of transits. So it's rare, and you have to stare at lots of stars to find one example of microlensing in a potential planet. The advantage, however, is that it's incredibly sensitive, and in principle, with good photometry, you can detect not just a Earth-like planet with microlensing, but a Mars or a Mercury or maybe even a moon-sized object, like an exomoon, which has never been found with the Doppler or transit methods. So that's the excitement of microlensing. And because it's a completely independent technique with its own set of selection biases and effects on the telescope that limit it, it's a cross-check on the statistics that we're learning from the Doppler and transit methods. So it's a niche technique, hasn't found too many planets, but it could find the lowest mass planets of all, and it's a cross-check on all our statistics. That's the fairly long-winded answer, but it's a fairly subtle and interesting technique. Next question.
We have a question from Aiden. He said, you said Kepler confirms 90% of exoplanets. What is an unconfirmed exoplanet?
The concern with Kepler is looking at transits, just to remind everyone, which is the momentary dip in the brightness of a star caused by the passage of a planet in front of it. So one reason Kepler might not confirm a planet is that the dip that it observes just turns out to be noise or a glitch in the detector. CCDs are not perfect. Cosmic rays could hit the telescope. There could be all sorts of things, surge in the electronics, who knows. Conservative astronomers will be very loath to declare a detection of a planet based on a single dip, because there could be other reasons for it. So Kepler, of course, looks to confirm a dip by the next time the planet comes around in its orbit. And to be truly conservative, it actually looks for a third dip. So there you've got two spacings that would match exactly, and you've measured the orbit. So when the 10% of candidate planets that Kepler does not confirm are a mixture of situations where a star, just actually had a flare. It's possible for stars to flare or for there to be a huge sunspot that rotates into the field of view and dims the star by a small fraction of a percent. That can happen. Or because of problems in the detector, just electronic noise or glitches. And so they're pretty cautious. But 90% is a pretty impressive confirmation rate. And so Kepler's 2,700 announced candidates should yield 2,500 confirmed planets given another year or so.
Gabriella asks, what will be expected with the James Webb Telescope to achieve in the quest for Earth-like planets and biomarkers on it?
That's a great question. So it's about James Webb and what it will contribute to Earth-like planets and their study. Interestingly, James Webb was conceived before exoplanets were discovered. The first designs of the James Webb, everyone knew the Hubble Space Telescope wouldn't last forever. So plans for a successor were in place as it was launched, essentially. Those plans have, carried on longer, and the project has ballooned in cost, as many of you have read in the newspapers. But so James Webb was not designed to do exoplanet work, but it has capabilities that can do that kind of work. Its advantage for exoplanets is that it's a near-infrared optimized telescope, not an optical telescope like Hubble. And the contrast between the reflected light of an exoplanet and its parent star is 10 times better in the near-infrared than it is in the optical, because the star's radiation is declining if it's a star like the sun, whereas the planet's radiation is increasing because it has temperatures of a few hundred Kelvin if it's an Earth-like planet. So it's 10 times easier to isolate a planet from its star with a near-infrared imaging capability, which is what James Webb will have. So that's its first huge advantage. Its second huge advantage is that it is a big telescope. It's a 6.5-meter telescope, and at those infrared wavelengths where it's predominantly working, space is an incredibly dark and pristine environment. It's easier to do deep infrared work from space than it is on the ground. Lots of infrared astronomy happens at ground-based observatories, but it's a little limited because the sky is bright at infrared wavelengths. It's typically infrared astronomy is sort of like trying to look at stars in the daytime sky. That's the analogy, and it can be that bad. So Kepler has those two great advantages. Its limitation is that the spectral coverage for doing biomarker work, so to retrace on biomarkers, biomarker is the attempt to characterize the atmosphere of an Earth-like exoplanet and look for molecules and atoms that indicate life or biology on the surface of that planet. And the classic biomarker is ozone and oxygen together. A secondary biomarker would, of course, be water vapor or methane, much of which is biogenic on the Earth. In the end, you'd want a suite of biomarkers. And that's the problem. James Webb has spectroscopic capabilities that are significant, but it can only look at very small bites of the spectrum, especially the infrared spectrum. So when James Webb looks for biomarkers, it's almost going to have to look one line or one band or one feature at a time. And that means it's really slow and it's going to take a lot of time. And then, of course, Earth-like planets are just really hard to observe. Even with that boost from the infrared reflectivity of the planet, you're talking about an Earth that's a few 100 million times fainter than its star. And even with a 6.5-meter telescope, you're not gathering much light. And then when you smear that light out into a spectrum, you're making it even harder to measure the intensity at each wavelength. When people run models of what James Webb can do, they predict exposure times or integration times of 50 to 100 to 150 hours to look for biomarkers of a single Earth-like planet. And to take your 6 best candidates, you're talking about maybe 1,000 hours of observing. That's an awful lot of time. And there's plenty of other astronomers that want to use James Webb for other things. So it's going to be hard for James Webb to put enough time into the biomarker project to achieve results or to look at a big sample. We're going to have to pick our best candidates and get a little lucky, I think.
Julian Onions asks, I've heard that astrometry is also a way to detect exoplanets, but not significantly?
Yes, astrometry, which is the measurement of positions on the sky. So typically you're making images with CCDs, wide field CCDs, and you're watching the motion, the apparent motion of objects on the sky, their positions changing. That's astrometry. So just as a giant planet causes a sun-like star to wobble, and we detect the wobble in terms of the Doppler shift, there's actually a physical wobble as well. In the solar system, the sun is essentially pirouetting about one axis, tugged by Jupiter. And so in principle, if we were watching the sun from afar, or our solar system from afar, the sun would not just sit stationary on the sky relative to the nearby stars. It would oscillate every 12 years by about its diameter. So that's the effect, and it's in principle just as good as the Doppler effect at finding a periodic signal due to a planet. You're looking at the wobble directly as a wobble instead of as a Doppler periodic shift. The problem comes when you remember how small stars are compared to the distance to stars. A light year is 6 trillion kilometers, and the sun is, round numbers, 1 million kilometers across. So you're talking about a shift on the sky of 1 million relative to maybe 10 or 20 trillion kilometers, and that's millions of times further. So the shift in the sky is millions of times smaller than the distance to the star. That's an incredibly small effect. You can do the math, and it turns out to be small fractions of a milliarc second. So it's sort of beyond or at the very edge of our ability to detect the wobble. In principle, in space, you can do it. And NASA has mission plans to put up imaging satellites, again, above the Earth's atmosphere, so the imaging is incredibly sharp and stable. And if those observatories, planned but not yet funded, unfortunately, were able to monitor hundreds of thousands of stars, 4 wobbles, it should find them. But that project isn't going to happen, at least for a decade, unfortunately. Yeah.
Aiden has another question that relates to moving into. Okay, wait, I'm sorry. I'm about to graduate high school and move on to Colorado Boulder next fall with a major of astronomy. Can you speak for a moment of what I should expect or things I should know going in?
So this is an issue that may apply to some of you out there who have an interest in astronomy and want to make it part of your academic career. The basic answer for someone wanting to study astronomy as an undergraduate is you're going to be taking a lot of math and physics. At my university, and I think this may even be true at UC Boulder, most astronomy majors are also physics majors. They're double majors. And in our department, 70% of our astronomy majors are double majoring in physics. So the basis of understanding astrophysics is physics. It's physics applied out into the universe. And so that's a good part of your diet as an undergraduate. And really, it's only in the later years as an undergraduate, maybe your junior and senior years, you start taking advanced astrophysics classes. And then if you transition to graduate school, you'll be taking almost pure astrophysics classes. So I guess the good news, bad news, I don't think there's bad news, but you have to like physics to be an astronomer or to study astronomy or astrophysics, because that's really a big part of it. And that's how most of us who ended up in astronomy actually started. My undergraduate degree from the University of London was in physics.
Bill Yohei asks, are there any favorite sites of yours that would go complement the course besides your own?
Sure, there's some good, there's some great astronomy sites. You know, for news stories, space.com is hard to beat. It's kind of, I kind of think it's cluttered with ads. It's a little bit annoying, but you know, I recognize these websites have to pay for themselves since they don't have a magazine that they can put ads in. So space.com is great for news stories. I also recommend the Bad Astronomer, Phil Platt, who does a blog with Discover magazine hosted by them. He writes stories and he does a lot of tweeting too, and he's extremely knowledgeable and he picks very interesting topics to write about. I mean, he just sort of provokes your interest with almost everything he writes about. So his blog is very prominent, and I think you find it through just Googling Phil Platt, P-L-A-I-T, and Discover magazine. So those are two. There are many astronomy sites. Of course, you have to get comfortable and familiar with the Hubble Space Telescope site, and not just the pretty pictures on that site. The Heritage Project is their archival images. That's the best of Hubble images, and I'm sure many of you are familiar with that. But Hubble is discovering new things pretty much every week, and they have their news section is filled with press releases that are usually written at a very intelligible level. They work. These scientists work with the press officer there to make sure they're understandable and clearly written. And there are literally hundreds of great news stories with accompanying pictures and sometimes animations and videos. So I would say Hubble and also all the great observatories, the Chandra and Spitzer websites all do very similar things. They make frequent news stories, typically once a week, of things being found with those telescopes. And the ancillary materials, the images and the animations and videos are great. So that's a small scattering. I think this is an important enough question that by the end of the course, or hopefully when we get some breathing space, I may put a list together of the best of the best websites in astronomy.
I have a question from Pete. Given that few exo-solar systems resemble our own, have any common ideas or theories been presented to explain?
So, very good question. The concern really is that after sort of rolling along thinking that our solar system was typical, because the Copernican principle says there's nothing special about any part of our situation in space, the first exoplanets kind of threw us for a loop, because there were so many of these hot Jupiters, there were eccentric orbits, there were there were some weird things going on, and the statistics have only just started to emerge. So a very legitimate question now, getting on for 20 years after exoplanets were first discovered, is how typical is the solar system? And the answer is we actually still don't know, because if you think about it, to find a Jupiter in a normal Jupiter orbit, excuse me, to find a Jupiter in a normal Jupiter orbit will take 12 years by any method, either dips or transits or Doppler effect. And to confirm that will take 24 years. And that's about how long we've been doing this. So we're only just on the point of finding giant planets in normal giant planet positions, and that's just Jupiter. Saturn, of course, is far enough away that there hasn't really been enough data to confirm a Saturn in a normal Saturn position. So part of the answer is we just haven't been doing this long enough. But it's also clear that some things are unusual. It does seem that most of the exoplanets have larger eccentricities than our planets. That is, they're in orbits that depart from circles by more than a couple of %. And that seems to have persisted. Another interesting phenomena is the discovery of what are called super-Earths. So the exoplanet game, as it pushes towards Earth-mass planets, one of the great goals of the game, has found a substantial number, probably 70 or 80, of what are called super-Earths, which is between 2 to 5, maybe 2 to 7 times the Earth mass. No such planets exist in our solar system. And so the fact that we're finding fair number of these super-Earths out there, many of which are on hot nearby orbits, but just the masses alone are not found in our set of planets, and that's starting to puzzle people. So those are two features of exoplanets as a cohort that differ from our solar system. But otherwise, I think there, in other aspects, the things we're finding are quite conventional. We're finding gas giants that have chemical compositions, as far as we can tell, that look very much like the Jovian planets in our solar system. The orbital properties are determined by Kepler's laws. I mean, no gravity law is being violated by anything we've seen so far. And the behaviors of the systems we found, because a lot of multi-planet systems have been found, they're all consistent with Kepler's laws, and the architectures of those systems are in accordance with our theories of gravity. So that's roughly what I can say on that.
David says, there is a net boost in acceleration of mechanical satellites by certain flight paths near planets. This appears to violate conservation of energy principles. Does it?
I think that's an allusion to the sort of the slingshot effect, gravitational slingshot. So I may have to revisit that question to be sure I answered it correctly. But if that's an allusion to the fact that it's routine in the space program to give satellites a boost in their momentum and energy to get them, for example, into the outer solar system against the pull of the sun's gravity, or to slow them down substantially when they're heading into the inner solar system, it does seem like you're getting something for nothing. But the gravitational slingshot effect does not violate any law of physics. Essentially, what's happening is you might send a satellite or a small space probe in its transit towards another destination near a planet, a large planet, or even a moon, and in its gravitational interaction with that planet or moon, it gains a little bit of energy. So it's just by a gravitational effect. But energy is conserved because that planet will lose that exact same amount of energy. So energy is transferred through a gravitational interaction to the spacecraft, giving it more energy, say, to escape to the outer parts of the solar system, and the planet loses that same tiny amount of energy. But when you think of how much more massive the planet is than the satellite or the rocket or the spaceship, it's obviously trillions or quadrillions of times more massive. And so the change in the velocity of that planet is undetectable, imperceptible. But yes, in principle, when a spacecraft comes along an object, say it's the Earth even, on a second pass, and uses the Earth's gravity to get out in the solar system, the Earth actually loses a tiny bit of energy and moves a very tiny bit closer to the sun. It's an unmeasurable amount, though. So no physics is violated there. It's just a very clever way of grabbing a little energy from a much bigger object.
Okay. Chris Miller wants to know more about the air pressure and especially the temperature on Mars. He heard it's really extreme near the surface.
The temperature, Mars is a pretty nasty environment. It's not habitable by most people's estimation. So the pressure of the carbon dioxide that's the primary constituent is about 1% of the pressure of the air we breathe at the Earth's surface. So it's a very, very thin, diffuse atmosphere. That means that, plus the fact that it's 50% further from the sun, which means it gets less than a half the radiation that the Earth does, means you're talking about temperatures of, depending on the latitude of the planet you're on and so on, you're talking about temperatures of minus 150 to minus 200 degrees. So incredibly cold. That's clearly far, far below the freezing point of water. The second thing that makes Mars uninhabitable at the surface is that very thin atmosphere shields and a very relatively weak magnetic field, because Mars is a small planet, mean that there's an enormous influx of UV radiation and cosmic rays, high-energy protons and electrons, say, from the sun, from the solar wind. And those particles hitting the surface are essentially sterilizing. So the best models suggest that the top centimeter or maybe 2 centimeters of the Martian regolith, the regolith is the technical name for the sort of pulverized, spongy, dusty material at the surface of a planet without a thick atmosphere caused by impacts. So by impacts over billions of years, the moon has a regolith, and the astronauts sunk into it, by a centimeter or so with their space boots and just imprinted perfectly the tread of the boots, because it's a very fine dust. Well, Mars has a regolith like that too, pulverized by micrometeorites and sterilized by high-energy radiation. So nobody ever would anticipate Martian microbes at or very near the surface. But further down, it's a completely open issue.
Aurora was wondering, is it possible that life on Earth originated on Mars? And do you think that we will have a manned colony on the Moon or Mars within our lifetime?
Both good questions. The question of are we Martians is also intriguingly open. It depends on multiple speculations, though. So the first speculation is that Mars was habitable and was indeed habited by microbes, say, 3 billion years ago, 3 to 4 billion years ago. All the evidence we've learned from the rovers and the orbiters suggests that there were standing but shallow bodies of liquid water on Mars 3 billion years ago, roughly. And so Mars indeed could have been inhabited then. And that habitability could have extended back to about 4 billion years. Now, so that's a speculation. We don't know the answer. The second thing about Mars that's interesting is because it's a small planet, the gravity is weak, and so it's fairly easy in an impact to eject rocks off the surface of Mars, easier than it is off the Earth, and much, much easier than it is off Venus, which is both Earth-massed and has a very thick atmosphere, so those blasted off rocks are unlikely to get through the atmosphere. So it's fairly routine for stuff to get blasted off the surface of Mars, and probably always has been. Those rocks, of course, have a tendency to move towards the sun, the gravitational source of the solar system, and so more of them will come inwards than outwards. And people have worked out what the flux of Mars meteorites or Mars rocks blasted off the surface into space is, and it's not trivial. And we know that we have at least 60 Martian meteorites in collections around the world, and they're of course representatives of probably thousands of Martian meteorites that have never been identified or recognized. So Mars rocks can get here. That's a speculation that's verified because we have Martian meteorites. Other scientists have shown that the interior of a meteorite the size of a small potato actually never gets much hotter than maybe 170 to 200 degrees Fahrenheit, even as it enters the Earth's atmosphere. So if a Martian rock was ejected with microbes inside it, because it had them at the time, they would survive both the passage through space, because in terrestrial situations we found, it's a little controversial, but we found evidence that microbes can survive perhaps up to 15 to 20 million years if they're interred in a suitable location. Essentially, they're just going to deep freeze. And then they would survive the landing on the Earth. So it's already multiply hypothetical, but yes, you could get a Martian microbe to the Earth intact. surviving the passage. And therefore, you've opened the door very slightly to the possibility that life formed on Mars first, maybe 4 billion, 3.5 billion years ago. Oldest evidence of life on Earth that's good is about 3.7 billion years. And that we're all Martians. That was the genesis of life on Earth. It's actually more likely for that to happen than the converse. It's more likely that life could get to the Earth from Mars than it could get from Earth to Mars. That's just a plausibility argument. I think nobody really understands how that could happen or think it did happen. If we find life on Mars, our test of that, of course, would be whether it's exactly the same biochemical and genetic basis as life on Earth. If it isn't, then the question is answered. That was a separate genesis. The second question asked was about whether we're really heading in our lifetime. It depends on how old you are asking the question, but let's just say 20 or 30 years for habitations on the Moon or Mars. You remember under a previous president, there was a plan for Moon, Mars, and beyond, which talked about habitations, and then budget reality set in, and the recession of 2008 happened, and space science budgets have not been healthy since then. So these are very expensive undertakings. Almost everything we know indicates that the Chinese will move swiftly towards putting their astronauts on the Moon, probably within a decade, this decade even. Almost everyone thinks that can happen. Remember, their budget for space science and astronomy are going up roughly 10% a year. That's doubling every decade, so they can do incredible things, and they've demonstrated their space capabilities. So the first habitation on the Moon might not actually be American. If the Chinese go there, for obvious geopolitical reasons, I think we'll go back and have our own base, so it'll be a miniaturized version of what happened in Antarctica, where the first explorers and the first countries to reach the poles established bases, and then other countries with territory adjacent to the polar regions insisted on having their own bases, so some version of that may happen on the Moon. But it's very expensive stuff. A Moon base is unlikely to be less than $100 billion to establish and sustain. Mars is harder yet, and whether that happens in 30 years is, I think, actually unlikely. So to get a Martian habitation, even the most minimal one, even one where the astronauts have committed to a one-way journey, and you've probably read in the news that private space enterprises are contemplating recruiting people for one-way journeys to Mars. It's an amazing thought, but everyone's going to die. Why not die doing something incredible like that? It is hard to imagine, but even with that in play, the technical obstacles to traveling to Mars are just huge. We've sent little spacecraft, and to send the life support for what in a direct route you do it in 4 months, but in the most easy trajectory for a spacecraft containing humans, we're talking about, for the return, a 2-year round-trip journey, and sustaining astronauts for 2 years is an extremely difficult and expensive thing. So I would say Moon base within 15 years, actually, just for the reasons I mentioned, and Mars base maybe within 30 years, but maybe not. People may get scared by the price tag.
Patrick Robinson wonders, how is it that we know a certain meteorite is from Mars and not somewhere else?
Yeah, that's a great question. We have a set of Martian meteorites, and they're cataloged that way, and some of them are very interesting geologically. And when people heard the story of the Allen Hills meteorite, which you may remember from 2005, President Clinton and the NASA administrator declared a press conference and with very splashy front-page news headlines, declared that scientists had found evidence of Martian microbes in this Martian meteorite. Now that evidence sort of unraveled over time. It just was never quite as good as people presented or thought. But the part of the story of that meteorite that was actually nailed beyond any doubt was the fact that it was a Mars rock, and that's true of the whole set of them. And the reason is simple. The rocks, these Martian meteorites, assuming they have to be found in a relatively pristine condition. If they've sat around on the Earth's surface for too long, like a geological timescale, they've probably been altered, contaminated by terrestrial material, and so they're not trustworthy. But most of the Martian meteorites are found soon after they fall, so they're not contaminated. All rocks of this kind, these are igneous rocks as it turns out, volcanic, have small inclusions. They have small bubbles, if you like, in the magma. And those are bubbles of Martian air. And so in a clean room or in a vacuum, you just take that Martian meteorite and dissect it and sniff the air that's in these tiny inclusions, these little trap bubbles in the rock. And then you can compare it to actually the first time we measured the Martian atmosphere, the Mariner and the Viking landers in 1974. And the Viking landers measured the abundance of not just of carbon dioxide that's a primary ingredient, but all sorts of radioactive isotopes and trace ingredients in the Martian atmosphere. And you can show that these little inclusions in a Martian meteorite match exactly the composition of the Martian atmosphere. Not just that they're carbon dioxide, but down to the details of the isotopes and the trace elements they match. There's just no way that could happen by chance. So it's beyond any doubt that they're Martian rocks. The tricky part, though, of the Martian meteorites, because you might say, having just talked about how expensive it is to go to Mars, why don't we just use the free samples? That's as cheap as you can get. They just land in our lab. The real problem with the Martian meteorites is twofold. First is bad luck. None of those Martian meteorites so far have been found to be sedimentary rocks. And in fact, sedimentary rocks are more frail, and probably when they are blasted off the Martian surface, they just obliterate into dust and don't turn into a rock that travels through space. So we'd love to find sedimentary rocks that came to Earth because we might find Martian microbes fossilized in those. The second thing that's a real limitation is that we don't know where the rocks came from. When a Martian meteorite arrives at the Earth, you can say what its geology is, but that never localizes it on Mars to anything other than one hemisphere or the other, or maybe one large region. That's critical because, as you probably know, when the Curiosity rover was when they were having to decide where to send Mars Curiosity rover, it was a 4-year-long process with huge debates and conferences as they argued down from 100 possible sites down to 25 and then to 4 and then to Gale Crater where it actually went, because they wanted to know exactly the geological and geochemical context of the rocks that it would study. With the Martian meteorites, you have none of that context, and that really limits their utility.
Julian Onions asks, if hot Jupiters migrate inward, what stops them from crashing into their stars?
Good question. So hot Jupiters are, to revisit the nature of a hot Jupiter, the first thing to remember is that we are very confident that they couldn't have formed there for 2 reasons. The main reason is just there's not enough material. Given that the solar nebula forms by collapsing and the planets essentially form in zones where they sweep up the material at their distance from the star, there's not nearly enough material in these inner orbits of a forming solar system to make a giant planet. So they could not form where we see them now. They have to have moved there. And most logically, they've moved from further out. And they did it very early in the history of these solar systems, maybe even within the first 1,000,000 years, or even within the first 100,000 years. So having started to migrate, why don't they just pile right into the star? And the answer is many of them do. So the hot Jupiters we see are the visible remains of a population, most of which did actually plow right into the star and add very slightly to its mass, because remember, a sun-like star is 1,000 times more massive than a Jupiter, so it can swallow a Jupiter like eating popcorn or something. It's not a big deal. Depending on the angular momentum, however, and because there is a lot of gas left over from formation, the gas acts as a dragging force on the giant planet as it moves in. And of course, it's sort of moving in a spiral pattern. And because of the spiraling in and the fact that there's residual gas there, which exerts a drag, it's quite possible dynamically for the planet to park in an orbit. And at that point, having sort of stalled, if you like, on its way in because of other forces, it becomes tidally locked, which essentially pins it to its position with one face of that giant planet facing its star. And it will probably stay there. That's a stable configuration.
Bob Brunstein asks, besides an impact event early in history, what other possibilities could have caused Uranus to tilt?
It could have been just an interaction.
Good question.
It's the question was about whether Uranus has an oddball tilt. It's tilted on its side essentially. Inclination angle is 87 degrees compared to the Earth's 23.5 degrees. So, yeah, as an aside, of course, that means it has extreme seasons. In an 84-year orbit, this is a planet with 42 years of winter and 42 years of summer. Now, those of you, I won't annoy people on the East Coast by telling you that it was 73 degrees and really pleasant outside, had lunch outside. But, you know, if you're on the East Coast and feeling sorry for yourself because it's still winter, you know, you could be on Uranus and there's a 42-year winter. So just, you know, deal with it if you're on the East Coast. You know, it will go away eventually. So brutal seasons on this planet, and of course it's incredibly cold so far from the sun. The impact hypothesis is almost impossible to prove. There's no archaeology, there's no historical record we can refer to. It's a plausibility argument. And it is almost equally plausible that there was a close encounter with, it could have been even a sun-like star. They wouldn't have even had to have been that close. That could have knocked, essentially gravitationally skewed this our giant planet onto its side. So it could have been interaction as well as a collision. It is almost impossible for the planet to form with that kind of a tilt because the angular momentum alignments in the solar system, which is to say where do the spin axes of all the objects point, are generally very tightly aligned, and it's really the exception.
Aiden saw something recently saying that dark matter may be weakly interacting massive particles. Can you explain?
So we're going to be talking about dark matter in detail in a couple of weeks. It's a big enigma in cosmology. It's the second most common ingredient in the universe behind dark energy, which is an even bigger enigma. But astronomers have had 40 years of measuring the existence of something that has mass but not light, and they call that dark matter. And in the process of trying to understand where dark matter is and how much of it there is, they've actually been able to rule out a number of explanations for dark matter. As we'll talk about in more detail in a couple of weeks, it's easy to rule out that it's not black holes, for instance. It's not substellar objects. An obvious thing you might imagine is, well, what happens? You get something smaller than 8% of the mass of the sun, and it never switches on as a light bulb, and then it fades to darkness. So that's a perfect candidate for dark matter. Or just space rocks, debris of all kinds in space going down to, you know, things the size of comets or asteroids. All of those things have been ruled out. The small things, interestingly, by the microlensing method. So I'd like to make a connection with one of the first questions we talked about. If the galaxy had 80% or more of its mass, much of which is in the halo at the periphery, in the form of small rocky objects, say, or planets, free-floating planets, just imagine anything you want that's smaller than a star, those objects in that abundance would cause microlensing signals. Because remember, there's more of that stuff than the normal visible stuff. So it's a lot of stuff, and there's a lot of microlensing. And the microlensing detection experiments using these big format CCDs were good enough in the mid-1980s to rule out that hypothesis. So we've ruled out a lot of things, and really the last viable option is a fundamental subatomic particle that is not observed in the physics lab as we speak, and is probably not part of the standard model of particle physics. So it's new physics. So in a sense, it's very exciting because astronomers have this big puzzle, very big puzzle. It's most of the universe. And particle physics has puzzles too. And the dark matter particle, if it is a subatomic particle, will be a solution to one of the biggest problems in physics as well as one of the biggest problems in astronomy.
David Jeffers asks, cosmic background radiation. Could you please clarify how radiation from the Big Bang is observable?
This also is a few weeks away for talking in detail, but just to set the scene, our confidence in the Big Bang as a theory of the formation of the universe 13.8 billion years ago is based on the expansion we see, Hubble's expansion observed in the 1920s and 30s. But probably the clinching piece of evidence, because it's so hard to explain any other way, is radiation that was found in every direction in the sky that's microwaves. That means very cold. It has an equivalent temperature of just under 3 Kelvin, 3 degrees above absolute zero. And this radiation is literally everywhere. It suffuses space. It fills the space between galaxies. It doesn't come from any astronomical object in the Milky Way or beyond. So it's a cosmic signal. It fills the universe. So what is that signal? It would have been completely enigmatic if not for 15 years previously. The discovery was the mid-1960s. In the late 1940s and early 50s, theorists used the concept of the Big Bang to predict that there should be leftover radiation from this hot, dense explosion. I'm going to talk about why it's not really an explosion, but I'll use that word just for the moment. So it was hot and dense, and the radiation that was very high energy early on, maybe gamma rays or X-rays, has thinned out with the expansion of space and cooled. And if you do literally a back-of-the-envelope calculation, because it was done by a physicist called George Gamow, an emigre Russian who spent most of his career in the United States, it was literally done on the back of an envelope. It's a simple calculation. He predicted that this radiation, after 13 billion years and the expansion of the universe by a factor of 1,000, should have cooled to microwave radiation. And so that prediction was made in the 1950s, early 50s, and then almost 15 years later was discovered. Those two things together are why astronomers are extremely confident that the Big Bang actually happened.
All right, so Pete wanted to know, can you characterize the useful range of detections for exoplanets given the 3 main methodologies in use? And what is the furthest super-Earth that has been detected to date?
So, good questions. So I'll try and do it briefly. I'll start with microlensing, the niche technique. Microlensing can find everything from a super Jupiter, 3 to 5 times the mass of Jupiter, which is the largest mass planets we've observed, literally down to Mercury. So it can find the full range in principle. It hasn't actually found the full range so far, but it can. The Doppler method can easily find the massive things because they have the biggest signals. And the Doppler method seems to be running out of steam or getting to a level where the noise really limits the measurement just above Earth mass, maybe 2 times Earth mass. Doppler method has found something of 1.9 Earth mass, and it's getting very hard to go less. The transit method, in the hands of the Kepler satellite, has already demonstrated it can go all the way up to the big planets because their dips, their transit signals are the largest, they're easy, all the way down to Earth and then even below. Remember, it doesn't measure mass, it measures size, but it can measure Mars size or probably mass planets. So it can go down to Mars mass, which is pretty impressive. The question of where the nearest super-Earth will be, that's a fascinating one, of course. The current hope is that it's Proxima Centauri system, that it's essentially the nearest multiple star system to the Earth, 4.2 light years away. We've already found a habitable zone planet. We've already found an Earth-ish, super-Earth mass planet, but not in the habitable zone in one of the stars in this system. That was a big news story last year. Subsequent observations are trying to find Earth or lower mass planets in habitable zone of one of those stars. So the best bet is actually is that it's going to be pretty darn close. As close as we could possibly hope for or imagine. Not hundreds of light years away, which is where most of the Kepler targets are, but right there in our neighborhood. That would be incredibly exciting.
This is going to have to be our last question.
Yeah, I think we're going to wrap up now. So one more question. Yeah.
Errol asks, it is exciting to find exoplanets, but what is the real value or significance of finding and studying them?
Good question to end with, a big question. Why do we do this? What's the value of exoplanets? I mean, at this point, it's body counting, because once you've found thousands, you sort of lose track, and it's a Guinness Book of Records thing of what's the lowest mass, what's the weirdest, what's the hottest, and so on. I think the value is that this research the discovery of exoplanets, and then soon after their characterization, which is the harder job that we're undertaking now, is the pathway to most likely answering in our lifetimes, and maybe even in the next decade, the question, are we alone? Is the Earth the only biological planet in the universe? And I think being able to answer that question scientifically within a decade would be extraordinarily exciting. And at some level, its meaning is just that it recasts our sense of ourselves, of our presence on this planet, and tells us that whatever went on the Earth 4 billion years ago was not a fluke. That biology has had its start on at least one other world, and if not, and if two worlds, then why not 200 or 2,000 or 2 million? So basically the game is on. As soon as we know that biology is not unique to this planet, a whole field of science has opened up, and that's really what drives a lot of the people doing this work forward. So we will wrap up for this week, and I'm happy to take, of course, your questions in this format and on the thread on Udemy. So thank you for participating, and hang in there and keep enjoying the class and letting us know how it's going. We'll try and keep up with the tide of material that we're committed to posting, and I look forward to hearing from a lot of you. Okay, goodbye.